So anybody have any questions? All right, well, I think what I'm going to do today is just go over a couple of derivations using the definition of mass moment of inertia to figure out the mass moment of inertia for some shapes. And then, like I said, mass moment of inertia, we're mainly going to use formulas, the same way we're going to use formulas for centroids. But I think it's good to have in your notes and good to see once or twice how this integral formula works. So seems like an okay time, like right before break. And then after break, we'll get into the more like practical applications, how you get this in a when you're really just doing a problem or whatever and not trying to show how mathy you are. So back to the mass moment of inertia. About a point. And it's just called the moment of inertia, but you need to keep all that other stuff in mind. And we're always going to call it capital I sub A, just like we'll always call the area moment of inertia in D form I sub A. And the integral definition of I sub A is the integral over the entire area. We're doing this in 2D, so all we're worried about is areas. Actually, I'm sorry. We're integrating this with respect to mass, so we have to do it over the whole mass. And the definition is r squared dm, where r is the distance from the about point to that infinitesimal bit of mass dm. And I'm going to do this show how this works for a disk, hopefully. So I'm going to do the mass moment of inertia of a disk about its center. But I want you to notice a couple things about a disk, because this is going to be an important thing to keep straight. So a disk, okay, so let me draw this sort of from the side, okay? Even though we're doing two-dimensional problems, you can have rotations about multiple axes in two-dimensional problems. So like, for example, the one that I'm going to do first is a rotation of this disk about this axis. Okay, let's call that the z-axis. But you could also do a two-dimensional problem where all your calculations are in 2D, but you need to know the moment of inertia of a disk about this axis. Okay, like so, um, a rotation about the z-axis here is like a wheel or a blade, or like a throwing star. A rotation about this axis is like a paddle, you know, like a paddle wheel or whatever, and you can easily imagine two-dimensional problems where everything's rotating in a plane, but the thing that's rotating is some kind of paddle, and you'll need to know that moment of inertia. And just the same way you could do it, so if this is the x-axis, then this would be the y-axis. So all of these have this same about point A at the center, but it's different calculations to figure out what the mass moment of inertia is about these axes. Okay. Notice that because of the symmetry of this disk, the moments of inertia about two of those axes are the exact same thing. Can you see which those are? So the moment of inertia about A rotating around the x-axis is the same as the y. Yep. But the mass moment about z is different. These are the ones that are like paddles. This is the one that's, I mean, it's like a wheel. I'm going to call it a blade because we're going to have to use this idea for other shapes too, rectangles or whatever. You have to think about whether it's trying to slice you or slap you as it rotates. You know what I mean? Okay, so let's do. Oh, I already wrote that, didn't I? Okay, so let's do the mass moment of inertia. Where A is the about point, about that axis Z, and we're going to use this definition. So over the whole mass of r squared dm. Okay, and since it's a uniform thickness all the way through, we can just think about sort of the mass density per area. So we'll divide the total mass by the total area, and then any area we multiply by the mass, that'll tell us how big the mass is of that piece. Okay, so the total area is just pi r squared, and let's call this a capital R to differentiate between that and the R in this formula. So the radius of this is capital R. And the mass of this thing we're going to say is m. Well, let's make that a big M too to differentiate. So the total area is pi r squared, pi big R squared. And so the mass per area I guess big M over A, is just big M over pi r squared. Okay, so now notice that what I've done here is I've given us a way to, instead of doing this all in terms of mass, which can be a little tricky to think about mathematically, now we have a way to represent this any increment of mass in terms of an infinitesimal increment of area, because we can just come up with our expression dA and then multiply it by this, and that gives us our dm. Okay, so who's with me on that? Nobody? Good. Okay, so dm now is equal to we want m over a dA. And so that is m over pi r squared dA. Okay. So now we can do this. The variable that we're integrating over isn't mass, it's area. And now we have to think about how we're going to break up this area into infinitesimal pieces. That's always like when you're using any integral formula, any integral definition, that's kind of like the heart of the problem, you know, figuring out how to break it up into infinitesimal pieces. So here's how I'm going to do it. So here's our disk. And here's our about point. And we're going to break it up into infinitesimal disks. Sorry, I guess that's not a disk. That's a like a ring or a washer. Yeah. Yeah. Yes, it's all the way through. When we calculated dm in terms of area, we turned it from a 3D problem into a 2D problem. So we don't even have to think about the thickness anymore. We can just think about it as 2 dimensions. But you also, yeah, right. You can just think about it as 2D. Okay, so what do we know about this ring? We'll say that the distance here is little r. Okay. And we'll say that the thickness is infinitesimal. And it has a value dr. Okay, so since this thickness is infinitesimal and this radius going to it is finite, we don't have to worry about, when we're talking about the distance from the center to here, we're assuming that that represents every point on this ring. You know, to get to the outside ring would be like, you could imagine it would be like r plus dr over 2, but dr is 0. This is finite, you know. To get to the inside ring, it would be r minus dr over 2. But again, that's just r. Okay. So how can we come up with an expression for the area of that infinitesimal ring? So this is our infinitesimal area. Yes, so that's what we're going to do. So what we're going to do is break this apart somewhere, stretch it out, and now it's just a long, infinitesimally thin rectangle. Okay. And so to calculate that area, it's going to be the circumference of that circle times the thickness. Okay. So dA is equal to 2 pi r dr. It looks like this once you stretch it out. you have a length of 2 pi r and a thickness dr. Okay, and we're just taking the area of that rectangle. That is a trick that comes up in in integral definitions of all sorts of things when you're doing circular shapes. And now that we have that, so we have dA, and the benefit of what we just did is now we have it expressed in terms of r, and look at the definition. There's an r in that definition that represents the distance from the center of the disk, or from the about point to the point that you're looking at. Notice that for everything that we have here, this is a whole bunch of points, right? But every one of those points is a distance r from our about point. Okay. So now we can represent this integral. So our I sub a is equal to the integral of r squared times dA, which is 2 pi r dr. We're missing one thing. We didn't want r squared dA, we wanted r squared dm. So we have to multiply all this by this conversion factor. So since that's a constant, we can pull that outside. M over pi r squared. And this one, you got to be careful with these r's. For that conversion factor from dm to dA, we're talking about the overall radius of the whole disk. We're not talking about that variable radius. So this should be a big R. So pi big R squared. Okay. With me on that?
R squared times dA times dm.
So it's r squared times dm, and we can re-express dm in terms of dA using this formula. The last thing we need is the bounds of integration. What r values are we going to integrate this over? 0 to big R, yep. You get a cancellation here. And so I sub a is equal to m over r squared. And let's pull the 2 out here too, that's a constant, times the integral of little r cubed dr. And so that's 2 big M over big R squared times little r to the 4th over 4, evaluated from 0 to big R. And so I sub a is equal to 2m over r squared, big R squared, times, plug in the big R value for little r, you get big R to the 4th over 4, plug in the 0, you get 0. And so this comes out to be 2 big M, big R to the 4th over 4 big R squared. And our final formula then is 1/2 big M R squared. So now we have this formula, you know, and that means that we never have to use this integral definition again for a disk rotated about its center. Any questions about that? Yes. Yeah, because the definition uses mass, but you just wouldn't want to divide by, you wouldn't want to express it in terms of area. You'd want to express it in terms of volume. Okay. So now let's figure out what happens if this disk is rotating like a blade. No, we just did a blade. If it's rotating like a paddle, okay, let's figure out what the mass moment of inertia is there. So this time, we're talking about a rotation about an axis like this. And again, we'll say that this has a radius of big R and a mass of big M. Yeah.
In the problems, when you say, when you give us the rotational axis, like when you, like in the problem, like the rotational axis is just an axis, it doesn't indicate which way it's spinning.
Yeah, it's going to indicate which way it's spinning, but we haven't talked about how that relationship yet. But basically, we're going to be doing all two-dimensional problems, okay? And so everything's going to be rotating in a plane. And so it just indicates the orientation of the object compared to the plane, kind of. So if you have a problem where, like, say it's a windmill, you know, and you have a problem where it's rotating like this, okay, then this rectangle is rotating like a paddle, not like a blade, and that has to be reflected in the mass moment of inertia. Okay, and if instead you have a machine like that's rotating like this, then you're going to have to use the idea of it rotating like a blade, not a paddle. Okay. Okay, so we're going to use this definition again. I sub A is equal to the integral over all the mass times r squared, little r squared, dm. And this is our axis of rotation. And so, well, again, let's calculate it. Let's do everything in terms of area and positions and stuff. So, question?
That's through the middle.
Through the middle, yeah.
That's a blade, right?
Well, that's the axis of rotation. So if you rotate something about that, it's going to be going like this.
Oh, I thought we just.
No, we did it like a wheel that's rolling down the street. This is like flipping a coin. I mean, I did draw a picture in the same plane, but the axis we did was coming out of the page in this one. We did Z, yeah. This would be X. Okay, so first, let's again express everything in terms of area instead of mass. And we can do that the same way. So dm is equal to the total mass over the total area times dA. So that's our connection between increments of mass and increments of area. And now let's define our dA like this. So let's take strips. Let's do it in X instead. So same idea, but let's do our strips like this. Okay, so our infinitesimal area is a strip like that, and then a matching strip. Oh, well, now we have to do it in relation to the axis. Oh, wait. It's not funny. That's not a circle. What? It's too late for that. Okay. So all right. So here's how we're going to break it down. We have one strip like that, and one strip that's the same thing symmetrically about that axis. And let's call this, so we have these two strips. They're identical, so this one has a thickness of dy. This one has a thickness of dy. And the distance from the axis to these two things, this one is y, and this one is also y. Okay. I mean, we could just do one of these, but I'm going to set it up so all you're trying to do is set it up in a way that you can represent all of the area using this idea. And so I have it set up with this symmetrical kind of approach, which just means that that in order to get the whole disk, all I have to do is go from y values from 0 to r, okay, instead of negative r to r. And so this double rectangle thing is our dA, okay?
Couldn't you just do the single rectangle as your dA and then multiply it too?
Yes. Okay, so what's the area of this shape? Well, notice that the length of that rectangle depends on the y value. Okay, so we need a way to represent the x that corresponds to a given y. And we can do that because we know that the formula is this for a circle. Who remembers the formula for a circle? X squared plus y squared is equal to, yep. Okay, so that means that x is equal to plus or minus square root of big R squared minus y squared. Um, and so the length of this, if I call this length L, the length of one of those rectangles is equal to, so notice this is like, what we have here is for a given y value, the x position of this end, okay? So you can think of that as half the distance, half the length, okay? So the length of the whole thing is going to be 2 times that, okay? So we'll write this length is 2 times that square root. So the area for a single one of those rectangles is 2 times this square root times dy. But we have 2 of those rectangles in our dA. And so our dA, remember that's for both rectangles, is 4 times this square root times dy.
Are we assuming that r squared is the constant? That the r is what big R means constant?
Big R is a constant, yeah. That's just the radius of that whole disk. And so now we can set this integral up. So I sub A is, so first we have our conversion to go from mass to area. So m over pi r squared, big R squared, times the integral of, now, what's the distance? So what we've done, the reason that I chose these 2 rectangles to represent our dA is because every point on these 2 rectangles is the same distance from the axis. Okay, so what's the distance from the axis of rotation to every point on those 2 rectangles? Y, yep. And so this formula, this integral definition, is y squared times 4 times the square root of r squared minus y squared dy. And what are the bounds of integration? 0 to y, 0 to r, yeah. So that when you get to, so the biggest y value you'll get is when you get all the way to the outer edge of that circle, and that's going to be big R. Y is equal to big R. Yep. Yes, you definitely could do it without doubling everything. Yeah. I'm just looking for, I guess I was thinking I'm going to look for the biggest infinitesimal areas that I can find where everything, the distance of all of those points can be represented simply as the same thing. All right, so hopefully we can do this integral. I sub A is equal to m over pi, oh, and the boundaries are 0 to big R. M over pi r squared times the integral, and let's pull the 4 outside. The integral from 0 to r of y squared times the square root of r squared minus y squared dy. So anybody have an idea how to do that? Trig sub. What? Yeah. Do you know what trig sub we would use? Okay, walk me through this. I haven't done this in a long time. You don't remember? Anyone? I'm going to edit this part out of this video. Me too. So let's see. R. I was just thinking if there was some way to do like just a U substitution. Jack, are you looking it up? Okay, pi. What did you get, Jack? Times r, and that's with those bounds? Oh, okay. R to the fourth. Yeah, so this is multiplied by 4m over pi r squared. Those cancel, and you come up with an answer of 1/4 mass times r squared. So for the disk that's rotating like a wheel, like a blade, it's 1/2 mr squared. When it's rotating like a paddle, it's a little easier to get rotating actually. It's 1/4 mr squared. And this integral is left as an exercise. That's what I always assume that people who make textbooks are like, I don't know how to do this. I'll leave it as an exercise. Well, I guess I need to review trig substitution. Anybody have any questions about that? So now rotating a disk like a paddle. Same thing as before. Like now that this has been done once, you never have to use that integral definition again. We just have to use the formula that we just came up with. Okay, that's all. Have a good spring break. I know. So yeah, I'll put tonight I'll put the assignment up for the week, but it's just going to be skimming through all the notes and writing like an outline of all the topics with the equations to just get yourself sort of centered on like where we are, what we've done, that sort of stuff.